Folks, welcome to Irrational Science. We're going to be talking about wormholes today. We talked about string theory the other day, strings, rings, because that's what they really are.
Irrational Science. We're going to be talking about wormholes today.
I had my sound going on where it wasn't supposed to. Anyways, I'm going to be talking about wormholes. And one thing I always forget to say is to hold your questions until the end, and we're going to try to answer your questions at the end of the lecture. You can ask any questions about the lecture or something else. It doesn't matter. Anyways, I'll be talking about wormholes. And what are wormholes? Well, we're going to find out today. And before I can get there, I'm going to give an analogy of that leads us into it, a sort of introduction, okay? And so let me start with that. It's got to do with art, and I think it's a pretty good analogy for what's going on in mathematics, mathematical physics, mathemagics as we call it, okay? And so we start here. If we go back maybe, 30 to 40,000 years ago, this is the kind of art you would find. You know, this is what they find on cave walls. So they were concerned about animals, I guess, and that's what they drew. Okay. Many centuries later, we're talking about now in the days of Egypt, maybe 3,000 to 4,000 years ago, right? You get, pictures of this nature. This is the type of art they were making, and it had to do a lot with the rulers, okay, with the people who ruled the country. Then you have maybe the Greeks. You could say maybe 300 to 400, even up to 500 and 600 years ago. This is what they were illustrating. They also made statues, right? They did a pretty good job on that. And I'm not including all the other societies and cultures such as the Aztecs and the Chinese and so on, right? There were other people out there as well. And by the time we get maybe to the Middle Ages, you get something like this. This is around the 13th century, okay? And what you get here is, again, portraits of kings. That's what they try to do. One of the main motives out there in those days was the Virgin Mary with a child. That was quite popular. You'll see lots of those around. By the time you get to the 16th, 17th century, they improved significantly on the pictures. They were doing portraits, and I guess that's probably the most famous one there, Mona Lisa. And, they were doing portraits primarily, and a lot of them were, the kings and rich people who wanted to leave a legacy. They wanted their future sons and daughters and granddaughters and so on to know who they were. And so they started getting pictures of this nature. There you have Henry VIII, and next to him, one of his daughters, right, Elizabeth. And you get other kings and princes out there. You have Charles II of Spain over there on the upper right, Louis XIV on the lower left, and so on down the line. What they did was make portraits of themselves so that they could leave something for the future generations. It turns out that by the time we get to the 19th century, early 19th century, we discover photograph. And that screwed everybody up because you get this case here, the heliograph of Georges Dumbois, and they took an engraving and they made a picture of that with some resist in the background, and they were able to make an imprint, a copy of that picture. Then you see, I think it was 1839 that Daguerre discovers the daguerreotype, right? And that's a picture of him 5 years later. Okay, so he He invented essentially photography, or they were, many people on Earth were trying to figure out, how to take pictures. And here you have good old Abe Lincoln, and he's, you can see all the different qualities. You have the painting, the daguerreotype, and the photograph. And, so you didn't need to have a painter anymore to go in there and paint these rulers, these important men. All you had to do was bring the guy with the camera, some kind of camera, right, and take a picture of them, and it was just as good or even better than the painting. So what happened at that point, portraits died down. In fact, I had a chat with an artist one day, and he kind of enlightened me because, I don't know much about art, and so I went in there and said, can you paint the Mona Lisa? And he said, no, I can't. And, he didn't have the skills to do that because they're not being trained to do that kind of art. A lot of people are simply not up to that level, to the level of, some of these people in the 17th and 16th centuries. And so, what do they draw? What happened to art? And he kind of enlightened me. He said, art's no longer portraits. That kind of art, that went away. So, art is no longer portraits. So what do they do? And you see this somewhat, to some degree, at the end of the 19th century. You get people like Van Gogh and Cézanne, and what they did was they created these pictures. Today they're worth millions, by the way. And what are these pictures? These pictures don't have the same quality as a Mona Lisa. It's like, painting a face, right? A portrait. But this was the art that supplanted, the portraits. They started doing, they looked at ideas instead of the quality of what they were presenting. And here you have something that came out a short time later, 1910s, 1920s. You have Cubism, okay? And again, what you see is, just ideas being represented, quite abstract, really, surrealistic. What is that? They call it Cubism, okay? So what is that? It's just a new kind of art that they had to invent because the portrait died out, making portraits of kings, the camera did that. We didn't need to, to have a painter do that anymore. Here you have a picture that came in this movement in art, Cubism. This wasn't Cubism, but it gives you an idea how abstract the art became. This is Guernica, that's how we say it in Spanish. And Guernica is about a battle, where Hitler essentially used his weapons, was trying them out for what was going to come shortly afterwards. And, what it is very abstract. It's about a battle. Okay, that's what the picture is about. But you can see that it makes no sense whatsoever. What is this? And, even in my worst days, I think I can, with a little practice, imitate what he's got there. I can't draw a Mona Lisa under any circumstance. I think I could probably draw this one, with a little bit of practice. Maybe it takes me a couple years. I can draw that stuff. It's nonsense. It's just the idea that's being reflected. And again, they're representing the idea, and they have this surrealism, this irrationality. Just, some of that is unimaginable. Okay, that's what it is. Here you have another one, and this one was sold the other day. It costs above 50 million bucks. They paid for this. Frida Kahlo's El Sueño, La Cama, The Dream, The Bed. And again, I think, with a little practice, I could probably even do this. Not that I'm any good at art, but, it's nothing out of the ordinary. It's just an idea being represented. And again, these things cost a lot of money today. Some people collect them for whatever reason. Maybe if they collect them to resell it and, have some value in it, That I can understand. But the guy who actually puts it on the wall and says, "Oh, I bought Kahlo's picture," I think he's out of his mind. I mean, there's no way I would put that thing on my wall, even if it was for free. Okay. Here's another famous one, and this was done by Salvador Dali. And this one's got to do a little bit with what Einstein and his buddies invented out there, which was time dilation. And so he had these clocks that melted, okay? And, this comes out the heels of special relativity a little later, but, that's what he was representing there. I guess this is, what it's all about. You have special relativity, and they say, we have something, I think they called it clock dilation or negative clock, just runs in the opposite direction. You have clock contraction if it runs too fast, and if it presses down on the scale too strongly, well, then you have clock weight increase, something like that. I mean, I don't know. Anyways, the art really matches the theories that are out there, and they're trying to paint the math, essentially. Then we have the opposite. We have, imagine, the mathematicians trying to get equations for art. The other way around, right? And here we have a mathematician, and he's going to try to paint a picture of souls going to heaven or to hell, either way. And there you have the equation. Okay, so we have an equation for souls going to heaven. You have equations for souls falling into hell. How's that for math and union of math with art? Okay, and here that's for motion, because now you got to make the equation for the motion of the soul going upward, the spirit or whatever, right? And then or down there, then you have the other guy that creates an equation just like, for string theory that we had the other day. Here it is. We have an equation for, all this cubism, these lines, these circles, these whatevers. Okay, so some abstraction, and you develop an equation for that. And then, of course, you have a fight between, those, because you have these two worlds. You have the world of souls going to heaven, and flying up there, and you have to look at the itineraries. Then you have the other guy who says, no, I'm doing equations for a different type of art. My equations describe lines and cubes and circles and whatever. And so, and they don't realize why they can't have one equation that can serve for both worlds. The world of the itineraries, the trajectories, and the world for, static figures, circles and cubes and whatever. And so this is more or less where math stands today. They have these equations that they have for quantum mechanics, they have equations for general relativity, but they want to come up with a single equation, the master equation, that can somehow synthesize both theories. And what's the problem? The problem is that they're developing equations now for abstractions. Just like in art, they moved into these abstractions that are unimaginable, they're surrealistic, and that's what we have in math as well. What they are doing now are developing equations for what? They're developing equations for strings. Do strings exist? Well, the answer you get is they haven't been ruled out. Okay, and they're developing equations, what? For wormholes? Why? Because they haven't been ruled out. Because people believe in them. Just like, people believe in souls. And so if you believe in a soul, right, that goes to heaven, and it's still alive, the idea is still alive, well, they develop equations for souls, and you say, well, why are you wasting your time on souls if they don't exist? If there's no such thing as a soul going to heaven or to hell. And they say it hasn't been ruled out because all the priests in the parish, all the churches, they still believe in all this stuff. And so, you work on the equations because people still believe in them. And they have these abstractions, and that's what they work on. And that's exactly what's happening with mathematical physics. They're working on abstractions on things that don't exist, things like strings, things like wormholes, and they're developing equations for it. And so, we arrive at here the equation for the wormhole. Okay, why did they waste time creating an equation for this nonsense that has no chance whatsoever to exist? And the answer is because it hasn't been ruled out. Okay, so that's where we stand today. The mathematicians are working on stuff that doesn't exist, that has no chance of ever existing, that has nothing to do with reality, with physics, with science, but they have to find something to do, just like the artists had to find something to do after, the portraits went away. And so they had to develop new ideas, and they went into what? Into abstractions, into surrealistic images, and that's what they paint, and they're worth more than the real art, which was, a real portrait of someone, which, I don't, again, I'm not an artist, I'm not into art at all, but I look at those pictures and say, that the guy who can draw that, a picture of a face so perfect as if it were a photograph, you take your hats off to that fellow. But to draw, this cubism, this nonsense that is just abstraction, you say, I mean, is that worth it? Would I put that on my kitchen room wall? And I don't think so. And again, if art has moved into that direction because it could no longer be doing what was really art, which was very high quality art, for something a little more real, like, a person, and it went into these abstractions, well, the same thing in parallel has gone on with math. They've developed equations for stuff that doesn't exist, for surrealistic stuff, because they had nothing else to do. They got bored doing the, standard calculus, algebra. They say, oh, that's so boring. I covered that in high school, and maybe freshman and sophomore years. Now I need something new. So they develop equations for all this nonsense. And that's where we are today. Okay, so what is this thingy called wormhole? What is a wormhole? And here we have a definition, okay? It says a wormhole, and again, this is from different sources. I try to look them up in different places to find out, exactly what definitions they have out there. It says a wormhole is a hypothetical tunnel through space-time. It's interesting to say tunnel through space-time, and what you're going to find out that that's not really true. I'll go with that in a minute. But it says that could connect two distant points, acting on a shortcut to travel vast distances in space and time. Okay, so what they want to do, they want to create a bridge, a tunnel, a kind of shortcut, so that you don't have to travel gazillions of miles, at the speed of light to get there. You have this shortcut. You cut across, space-time. That's what they're saying. That's what this is going to be about. It says a wormhole is envisioned as a tunnel with two ends, each connecting to a different point in space-time. Imagine the universe as a flat sheet of paper. A wormhole would be a way to warp that sheet so two distant points touch, creating a shortcut. By creating a shortcut through space-time, a wormhole could dramatically reduce time travel time. For example, a journey that would normally take millions of years could potentially be completed in minutes. Okay, but see, you can see that the wormhole is like a separate thing from space-time as it's shown down at the bottom. It's like, are we talking about a distinct thingy that is not part of space-time? It goes through space-time. It's in space-time, like if it's some other object that's in there. That's the point, okay? And the answer is really no, but here, let me show you what these people are saying when they say that they're going to connect the dots, right? Here you have two dots, okay? And you can see there's a separation between them, a distance, a length between them, whatever you want to call it, distance traveled. And what do? Well, they fold them. They fold it, and there you have it. The dots are touching each other. Essentially, that's what they're doing. And you're saying, well, I mean, is this surrealistic? What are we talking about here? What is this? You can go with your car, and you don't have to drive because you bend space-time and you're already there. I mean, what is this? Is this real? Is it physics? It hasn't been ruled out. That's the answer. So, yeah, this is the problem. The problem is that who didn't rule it out? Well, the mathematicians. Physicists never even accepted it to begin with, but these people not only have entertained the new idea, this surrealistic idea, but they say it hasn't been ruled out, mathematically, of course, right? So here's one of the problems with that, okay, and that's the fact that, those number lines that are bent there, what they're doing in the wormhole is made of these same number lines. It's not like the wormhole goes through or crosses or perforates space-time. The wormhole is space-time. It's bent space-time. And you can see there I bent it upwards because you can see all the bottom ones on those three wormholes. They're all moving upwards, okay? And that's important. It's important because they always illustrate the space-time downwards, with a mass sitting on it. And so people understand, they say, okay, I understand why it's downwards because the weight is pushing the net downwards. But if they illustrated this more often, like upwards, maybe a lot of people would ask questions and say, what do you mean upwards? I thought gravity was downwards, right? And that's the issue. The issue is they always illustrate the fishnet, right? Downwards. Which is cheating. They should, because there's no orientation in space, and they know that, and so they can't always illustrate it downward. They should illustrate it upwards, so that it'll call the image will call it to people's attention that something doesn't seem right. What do you mean? Weight pushes it upwards? What is that, right? Okay, but this is the standard version of a wormhole. And this is also cheating because they're saying that the wormhole is really mouth to mouth. It should be like this. It should be the opposite direction because what you have is the mouth of one wormhole touching another one. You cross it and you're already, in a different universe. And so these people cheat in many ways with their images, and it doesn't match what they're saying. That's my point, okay? Okay, so why did we need these wormholes? Why were they invented? Why were they created? Why did anybody waste time, developing these equations for this so-called Einstein-Rosen bridge, right? The wormhole. And here's a very brief history of that so that we can put it in the right context, okay? Here it is. 1935, Einstein, Podolsky, and Rosen wrote their EPR, that's EPR for Einstein, Podolsky, Rosen, right, paper, which challenged the completeness of quantum mechanics, okay? Albert Einstein and others, right? That's the name of the paper. Can quantum mechanical description of physical reality be considered complete? Well, the guy who was offended by this was obviously Niels Bohr. And so he had to change this. He said, I'm going to write a paper against that. So he wrote a paper criticizing Einstein, Podolsky, and Rosen, the EPR. And in the same year, just in fact, a couple months afterwards, and so they had this debate in their published papers. And then again came Einstein and Rosen this time around. They came up with their ER bridge, their wormhole, essentially. It wasn't known as a wormhole then. That came later. But the point is, they just kept answering. Bohr answered Einstein, and Einstein answered Bohr. That's essentially what happened here. And what you have is the Einstein-Rosen bridge solution attempted to address what? Quantum mechanics non-locality. That was the issue because they said, look, we think that there's some hidden variables out there, right? And that was later on allegedly, debunked, but that was the proposal, that there was something else going on that quantum did not account for completely, and that's why they said it's incomplete. Something's still missing, you know. And Einstein, again, he didn't like quantum at all. He used to say God does not play dice, right? And so, again, the folding of the sheet is how he fixed it. So he developed an equation based on general relativity, in which, you know, they were able to say, well, you know, we can essentially explain entanglement here, because the equation allowed him to do that. And here you have, on the left there, you have good old Niels Bohr. He was towering over poor Einstein. He was being trounced at the meetings and so on. All the mathematicians went with Bohr instead of with Einstein. But everybody gives credit to Einstein today, and a lot of people don't even know who Bohr is, right, out there. But everybody knows who Einstein is. Anyways, here we have Stephen Hawking, and he clarifies for us that, you know, the wormhole now today, after they've developed these equations, allows you to travel through space in 1 second from here to another star or to the other side of the universe. All you have to do is get into a wormhole. And here he clarifies, he says, closely related to time travel is the ability to travel rapidly from one position in space to another. So we're talking about space here, right? Traveling through space. Through a wormhole, obviously, right? That's what he's going to talk about here. So the only way to get from one side of the galaxy to the other in a reasonable time would seem to be if we could warp space-time so much. He's going to warp space-time, right? The fishnet, what are those? Number lines. That's what they are. So much that we created a little tube or wormhole. Okay, so he's going to create this wormhole. Essentially, he's warping space-time. He's warping the number lines. That's a mathematical concept that he's warping there. But they get away with the stuff and say that it's physics. And says, you could travel back in time with a wormhole. This could connect the two sides of the galaxy and act as a shortcut to get from one to the other and back. So Stephen Hawking actually believed in all this stuff. You know, it's not like they're just doing math for the sake of math, which is really what they did. They developed math, irrelevant math, irrational math for stuff that doesn't exist, that has no chance of existing, but they always fix the problem by saying, well, you know, it hasn't been ruled out. That's the famous phrase that they use. Okay, so good old Stephen Hawking, he continues. He tells us about what is required to make this wormhole. He says, one can show that to create a wormhole, one needs to warp space-time in the opposite way to that in which normal matter warps. Ordinary matter curves space-time back on itself like the surface of the Earth. However, to create a wormhole, one needs matter that warps space-time in the opposite way, like the surface of a saddle. Okay, so now you know. Don't do it like a ball. It's got to look like a saddle. Okay, and now you're getting close to what a wormhole is. The same is true of any other way of warping space-time to allow travel to the past. Okay, so he's going to mention also time, but he's talking specifically about space right now, about distance, right? We have experimental evidence. Experimental evidence. Yeah. What is experiment for? To collect evidence. What is evidence for? To persuade, convince, and recruit people. That space-time is curved from the bending of light. Okay. So what they're going to try to do is not explain to you. They're not going to rationalize this theory for you. What they're going to do is try to convince you. And for that, they bring, proof, evidence. Says, we got it from the experiment. So they know for a fact that space-time is warped, they can be bent, and it turns out that, where did he get that from? I mean, what are we talking about? What's being bent? Number lines. Number lines are mathematical concepts. They're bending these number lines, and that's the explanation they give for gravity. And that's what they're going to now extrapolate and use it for the wormhole, just like they use it for black holes and even dark matter, right? Okay, so what is needed to be able to warp this space? Well, hold on to your hats right now, okay? It's going to get dangerous. And he says, one would need matter with negative mass. Negative mass. Boy, a lot of chubby people would like to have negative mass, and negative energy density to make space-time warp in the way required. Quantum theory allows the energy density to be negative in some places, provided it is positive in others. In other words, you have this, the second law of thermodynamics that, you have to balance the account in the end. And that's what he's talking about there. He says you can have negative energy over here as long as you put some positive over there, right? That's what he's saying. The reason quantum theory can allow the energy density to be negative is that it is based on the uncertainty principle. Heisenberg's indeterminacy. Okay? Fields can't be exactly zeroed. If they were, their value would have both a well-defined position at zero and a well-defined speed, which was also zero. This would be a violation of the uncertainty principle. See how they fix these problems? With all this nonsense, this double talk. They say we have uncertainty principle, right? What is the uncertainty principle? Uncertainty principle says that if you have a ball, right, and the ball doesn't move, well, then you know a lot about its position, its location. But you know nothing or very little about its motion, its momentum, right? And so if it moves, now you know a lot about its momentum, its motion, and you know nothing about its position. Yeah, no kidding. So that's what Heisenberg invented. And that's what he's using as a basis, as a foundation, to justify why, you have this rule in wormhole land. Okay, so what is he saying? Well, here we have a little illustration of what of what Stephen Hawking is saying. Okay, you have a man, and he's going to go to his home. And so he takes this long trip through space, right? Because now we're talking about space, right? So he's going to walk from one place to another, right? Going into his house, right? And he's taking the long route. And what these people are saying is you don't have to be such a inefficient individual. What you have to do is do it like this. Here you have the same man, okay? And that's a starting point. And what you do is you divide the universe in half. Diagonally, but that's irrelevant, right? You divide the universe in half, and then the way you do is you bring the house together with a man. And there you have what a wormhole is. All you have to do is bring the door to the nose of the man, and you've got it solved. And so he doesn't have to spend all that time going through space. He can do it in 1 second by just bringing, the house close to his nose. Now, is that rational? I mean, you can do that in mathematics. You can do anything in mathematics. Like we used to say in engineering, we used to say that we said it with statistics. With statistics, you can prove that an elephant dances on a pin. You can do anything. Does that mean that you can do that physically? The answer is we can't rule it out. We haven't ruled it out. Okay, so this is where we're at today. They don't rule anything out, and all they're doing is equations for inexistent stuff. And here we have the time travel. One fellow kind of regurgitates what Stephen Hawking said, and all these other fellows, and he says, you can use this for time and for time travel, and that's exactly what it ended up being. The wormhole, originally created for explaining how one particle, one side of the universe, can connect to another one, because Einstein and Rosen were trying to debunk quantum mechanics. What they did, they took all that, the equation, and what they're using it is for time travel. And there you see, this fellow says the following. He says, the central reason for ongoing discussion of wormholes in their potential application in teleportation and time travel. That's what it's used for. And as sci-fi as this sounds, the possibility hasn't been conclusively ruled out. Yeah, they keep saying that it's not ruled out. What do you mean it's not ruled out? Ruled out by whom? Rationality rules it out. Math may not, but rationality, rules it out. It's nonsense what these people are doing and developing there. Therefore, it is valid if speculative theoretical physics question. So they think this is a valid thing for a physicist to be investigating, to do equations on inexistent stuff, on irrational stuff, surrealistic stuff that can never have the possibility of existing, of even materializing. This is total nonsense of going through space and 1 second and you're on the other side of the universe. This is just to give hope to people who say, will we ever get to the nearest star? Sure, all we have to do is just go through a wormhole. That's what they're doing. They're just giving hope, false sense of security, really. They're giving hope to people, saying, we can travel throughout the universe just going through wormholes. All we have to do is, as you're going to see, is just keep it open, keep the wormhole open so that we can go through there. What do you do that with? Negative energy and something called exotic matter. Ooh, whatever that is, okay? Anyways, no, this is not speculative, theoretical physics. Got nothing to do with physics. But this is what these people are working on now. And there you can see, you're in 2025, you want to visit Napoleon in 1815. And, the astronaut wants to go there. And all he's got to do is drop through a wormhole and he's there. Okay? That's how easy it is. Why didn't we figure this out since so many centuries ago? So easy, all you have to do is cheat. I mean, if souls can go to heaven, why can't, astronauts travel through wormholes, right? Okay, so here's one of the persons who worked most on this, and that was Kip Thorne. And what he was called in by Carl Sagan for a movie that he was making, and he says, you got to help me out with this. And so Thorne went out there, started studying the wormholes, consulted some of his colleagues, and he came up with all kinds of nonsense. He says, yeah, it is possible to travel through a wormhole. All we have to do is make sure we keep that, that wormhole open, okay? And so this is what he's got to say. This is an article that came out in Science Magazine, and it talks about Thorne's theory, essentially. He says he's got a wife, right? Thorne's wife hops aboard a spaceship. They can see each other through the wormhole, okay? They can even hold hands. So there you see them holding hands, right? Each one on different sides of the wormhole, right? That crosses all of space-time because one is one side of the universe, the other one's on the other side. So they're shaking hands through that wormhole. And that wormhole is really quite a, I guess Alice in Wonderland kind of hole, Anyway, they can even hold hands as if through an open doorway. His wife travels a round trip 12 hours at the speed of light. Okay, so she goes and comes back, say 12 hours later, right? Thorne sees his wife return from her trip, but when he looks out the window, his front lawn is empty. Why? What was 12 hours for her was 10 years for Thorne back on Earth. His wife has landed on Earth 10 years after she left. There she will meet Thorne 10 years older, but she can still reach through the wormhole and find Thorne, who is only 12 hours older. Okay, so she shakes hands. She never left his hand, right, through the wormhole. For her, only 12 hours have gone by. For Thorne, there's been only 10 years gone by, but they're holding hands. And then comes the punchline. He says Thorne can step through the wormhole and find himself 10 years in the future, or his future self can step back 10 years into the past. I mean, what does any of this have to do with physics? This should not even be, it should not even be published. These people want to do nonsense, they want to go to Hollywood and have them make a movie of time travel, that kind of thing. No problem. But this has nothing to do with physics. Why are they bringing this into science? And they say, well, it hasn't been ruled out. What do you mean it hasn't been ruled out? Ruled out by whom? Who accepted this? Who were the peer reviewers who allowed this stuff, this nonsense, this poppycock to be published? This should not be in any scientific literature. Forget it. And we talked the other day about the block universe. Okay, and there we had these slices that Brian Greene told us about. He said we have all these slices of time, cross sections of the loaf, which is essentially the block universe. And the question is, we question this because there is no such thing as a slice of time. Okay, you need a couple of slices to have time. One slice only has location. Okay, you have every atom in the universe there in a single slice. None of them move. If you want them to move, you got to have a second slice, and only then can you have time. So this is, again, a misrepresentation of what time is. Time is not a slice. You cannot synthesize time or motion in a single slice. Cross-section of, every atom in the universe in that slice. That's all you have there, okay? And so, yeah, it's a misrepresentation. And so here we have a good old astronaut. I showed this the other day. We have the astronaut, and the astronaut's going to fly to through the tunnel or through whatever means, right? He's going to go into the past. He's going to be he's going to try to shake hands with Napoleon. So here it is, okay? You can see the astronaut. He's going to take off, and he's going to go to 1815, and he's going to talk to Napoleon there, okay? That's what these people are saying. They say you can do this, but see, that slice of time is wrong for a couple reasons, and the main one being, that you cannot have a slice of time. That's one issue. The other one is that all the atoms have moved and are now in the present. Okay, and we showed that through the Universal movie. See if I can find it here. Where is it? Here. Here's the Universal movie. Okay. There we go. And what you have is a single frame. And all the atoms in the universe are in that single frame. They were in the past, in the one on the left, the previous frame, but no longer there because they all moved. Every atom moved to the new frame. If they were still in the previous one, in that blank one on the left, well, we'd be in a hell of a trouble because that means that there is no motion in the universe. All you have is duplication. What you have is cloning of every atom in every single frame. That's the only way you can go past, to the past and land on an atom of some kind, because that atom what happened was that atom just made copies of itself in every single frame of the film, and that's not true. That's all we have is motion of atoms. That means that at any point in time when we get a cross section of the movie, all you're going to have is distance between every atom in the universe. What you have is location. All these are static concepts. Okay, you have existence. You don't have motion. You don't have time. And so you can't have a single frame with time in there. Okay, and so this is part of the problem. And here we have the astronaut again trying to get through the wormhole. Okay, and where's he going? Well, he's going to try to see Napoleon. Okay. And what's the problem with that? Well, again, the problem is they're going through space-time. How are they doing it? Through the wormhole. But the wormhole is space-time. Wormhole is bent number lines, warped number lines. Okay, it is space-time itself. But see, they put it as if, it's something separate from space-time. They say the wormhole goes through space-time. What do you mean? If the wormhole is space-time, how can it go through space-time? So we have a problem there as well, okay? And here we have Brian Greene. He's going to teach us how to jump into a wormhole, okay? He's going to jump in there, and he's going to talk to himself early in the morning. In fact, he's going to shake hands with himself, okay, earlier that morning. So he traveled back in time, through the wormhole. Okay, this is how he does it. And you're saying, is this possible? And what is that wormhole? What's the tube? That tube, that tunnel, what is that tube? Well, it's space-time itself. So what is he traveling through? He's traveling a hole in space-time. What is the hole? We have a problem because space-time is the wormhole, and wormhole is the space-time. So these people are cheating because they're saying that the wormhole goes through space-time. And so even if that were true, that you've got a hole through space-time, what is that? Is that a nothing? Are we talking about nothing going through space-time, that you're keeping that wormhole open, there's nothing there? Okay, what is in there? And so they had to create this nonsense that, you have negative energy and you have exotic matter. And again, all that has to do with negative signs in mathematics. It's got nothing to do with reality. And they had to create these new concepts. So, I mean, if you saw this, here you have Mary Poppins, right? And she's going to do a little bit of magic. Okay, here it is. I'll show you her in a second here. Here you have it. Okay, so if I show you that, you say, well, but that's science fiction, that's fantasy. Well, what's different between that and jumping into a wormhole and ending up early in the morning shaking hands with yourself? I mean, at least Mary Poppins, she didn't shake hands with herself. She ended up in a different time and place, right? Different space-time, right? And we say, oh, but that's fantasy. That's science fiction. That's not science. But which is even worse, which is more irrational, they call it science, they call it physics. So we have a real problem here, I mean, if you think that's science, well, I don't know what to tell you. And here's the punchline of all this, and that is that you would think that, well, okay, who pays attention to wormholes? Well, here, let me show you. These are the papers, some of the papers, I mean, these are not all, that are in the archive. Okay, and all these people are investigating and developing equations for all this nonsense. Okay, they're developing equations for wormholes, and you're saying, can it be possible that all of mathematical physics has gone irrational, totally irrational? That all these people are working on wormholes, they're working on string theory, on the rings. They call them strings, they're rings. And what are the rings? Well, they're one-dimensional, meaning that you're talking about locations, meaning you're talking about motion. The ring is not a ring, like this would be a ring, right? This is a ring. That's not what a string theory is, the string of string theory, the closed loop one, right? No, this is not what it is. What they have is something going around, locations going around. That's what they have. And so they're developing equations for a string that's made of 1D line, they call it. What is a 1D line? It's an itinerary made of locations, okay? And that's what they're doing in string theory. Then they take that little thing, they turn it into, a ring, and the vibration of that thing is supposedly a particle. And from there, they move on to doing gravitons, and they say, oh, the gravitons move and produce attraction. Well, even if I had many of these, how do they attract? I mean, even if they vibrate and do whatever they have to do, how does a discrete entity like this one pull on something else? How do you explain gravity with it? And what does this have to do with space-time? I mean, what's the explanation for gravity in general relativity? The warping of space-time. It's got nothing to do with a ring. Okay, so again, they're trying to merge equations of ideas which cannot be merged, which are contradictory, completely contradictory. And the wormhole is in the same boat, because the wormhole is what? Trying to unite general relativity, space-time, warping of space-time, because that's how you make a wormhole. And you're going to connect, I mean, what was it designed for originally? You're trying to connect particles which are entangled. One can affect the other one through what? What's the mediator? The mediator is the wormhole, meaning space-time, meaning we're going to merge quantum mechanics with general relativity. And so they're developing equations for that of stuff that is totally inexistent, that has no chance whatsoever of ever existing. It's not even possible. Not even God can imagine what these people are talking about. You cannot really illustrate it because what they're doing is cheating. They define one thing and they illustrate another, and they don't care about the images. What they care about is their equations. And so we have all these mathematicians, and they're working on wormholes, and you're paying for it. So, that's the world we live in. What can I say? Anyways, see if we have anyone who wants to ask questions either on the material we had today or any other issue. If I can't answer it today, I'll give you a rain check and I'll, put the question again in the comments section. I'll try to answer it. Okay. Give you 10 seconds. Okay. If anyone wants to ask a question. Okay, I guess I'm going to skip then and just put the question in the description or in the comment section, and I'll take a look at it.